So, for example, instead of looking at pictures, you might be asked to draw pictures like that. Okay, so sometimes, sometimes that way is just as important. Okay, so let's continue with this, which is, so it's about integration, reversal of differentiation, a big deal. So there is no point of just sticking with the one and then suddenly realize that it's less than half of the story. So this is the picture of gonna continue on in calculus, and really there is no way to avoid it, only to postpone it. So we're not going to do the whole thing just yet, but to be aware of the problem, and you already are able to solve a lot of problems of integration based on entirely on nothing but the your knowledge of differentiation, right? So if you have differentiated once, so that pair of functions already has been established to be related to each other in that way. Function is derivative. Okay, now you know that it is also the same pair is related. The relation is the same, but you can call it differentiation from left to right, anti-differentiation from right to left. Okay, so and what's at the very bottom is once we get after the test, we'll talk about the projects, and once again, if you talk about any kind of projects, it is the reversal thing. And so I hope you remember the way numerically we have done it a few times. How from acceleration you get the velocity, from velocity you get location, and it can be a specific function, and it often is, such as say my acceleration is what is it? Negative 16 feet per second squared. Okay, so thinking backwards, what is the function, the derivative of which is negative 16? What kind of function? First question, what kind of function is it? What kind of function the derivative of which is constant? Derivative is constant means that the slope is constant. The slope is the same throughout the function. What kind of function? It's a linear function, right? So it's a linear function. Every time you integrate a constant function, you know you're gonna end up with a linear function, and then it just remains to figure out what the coefficient of the function is, and it is negative 16. So it's negative 16 x. Well, let's say t, so that we're talking about time. Okay, and then remember the ambiguity of anti-differentiation. So there is that extra term here, which is, let's say, I call it, say, x, v naught, v sub x. Okay, v sub x. So initial velocity. So you don't know what that Vx is from what the setup is, but it's not the bad news, it's the good news. It means that you have taken care of all the possible motions as patterns of motion, as long as the acceleration is negative 16 feet per second. So all the possibilities are there. Then you don't stop here, and then you make one more step, and now you ask yourself, what is the what kind of function the derivative of which is negative 16t plus Vx, which is just a number. Well, when in doubt, think power function. These are we're not dealing with any complexity of function. These are all powers. These are all powers, and you know what happens to the powers when you differentiate. With the power rule tells you what happens to the power when you differentiate. It goes down by 1, right? So when you anti-differentiate, it will go up. It just did, right? Constant degree is 0. Linear degree is 1. One more time, degree is 2. In other words, it's a quadratic function. The only thing that remains to figure out is what that coefficient is. So it's really going to be t squared. What is the coefficient? If you differentiate t squared, you're going to end up with 2t, and instead of you have negative 16. So to adjust it, you put here what? It's actually not. Hold on, I think I messed up. It's actually 32. Yeah, the acceleration of gravity is 32 feet per second. So, and then now we have negative 16. Okay, and then that is there's an extra term there. Okay, fortunately we know that differentiation satisfies the sum rule, which means that we could just as well integrate that term Vx separately. And so we already know how to integrate something that is constant. So what's the term? I integrate Vx, which is just a number.
C.
What?
C.
No, just yet. Vx is a constant on the right. So the question is again, if I differentiate, what function do I differentiate? No, it will be Vxt. When I differentiate with respect to t, Vxt, I'm going to end up with Vx. So that's again about the power of t that changes from 0 to 1. Right? It was Vx power 0, now it's power 1 linear. Okay, and then there is an extra term here. It will be, say, I don't know, p sub x. That is initial location. Why do I put x there? Because we're going to do next, we're going to, sorry about that, that's supposed to be a y. Sorry about that. Because we're talking about the vertical motion, so this is all about y. So vertical gravity pulls us down, negative 32 feet per second squared. Okay, then we integrate once, we have negative 32t plus vy, where vy is the initial vertical velocity. Okay, and when we integrate one more time, there is that extra constant that appears every time we integrate, and it is I call it py because this is our initial position or initial location, once again vertical. So this is all about y. This is motion with respect to the y coordinate, and there is that's all there is. So backwards thinking is one way, just relying entirely on your experience with differentiation, or we do have already formulas. They look at the very top in red. In fact, that is how we integrate power functions. So functions on left, antiderivative on right. So you can see how power goes up by 1, and extra term over there, 1 OS plus 1. Okay, so that's exactly what has happened here. That's where if I do t squared, integral of t dt is t squared over 2 plus c. Okay, so the power is 1, goes up by 1, and then it also appears in the denominator. Okay, so that is the equation of a free fall. Our position at time t is given. Let me write it like this: x of t. X of t is our position or location as a function of t, and those the gravity appears is negative 16. In the meantime, and as you can see, it sort of increases as t increases, changes your position in a quadratic way. And in the meantime, the two parameters that your motion depends on, the initial velocity, initial position, are also there. Okay. Well, let's take x. What's the acceleration in the horizontal direction? So I'm throwing an object. What's the acceleration horizontally? In other words, what's the force? Accelerations come from forces, so what's the force?
Stay the same. The constant number.
What's the force?
Velocity.
No, the velocity is velocity, force is force, and acceleration is what's the force? What's the horizontal force? The gravity pulling down. What's pulling or pushing horizontally?
Inertia.
No, it's not a force. It's a trick question. There is no force.
So it wasn't.
There is no horizontal force, right? There is the free fall. That's exactly why it's called, because there is only one thing that is involved, affects it, is the gravity, and it pulls down. There is nothing happening horizontally, right? Okay, so going the same way. So what about the velocity? Now this time horizontal velocity. What is the function derivative for which is 0? Functions with a 0 derivative.
Is it a constant?
It is a constant, yes. And I put here a constant function. I put here v sub x. So that is a horizontal initial velocity. Okay? Initial velocity vertical, dy, and this is once again. And then we're doing something that we just done. Now integrate one more time to find our horizontal position as a function of time. So what do we get? Integrate constant, what do we get? We just did it. A constant function. How do we integrate a constant function? Is linear. Okay, so it will be dxt plus p sub x. Initial horizontal location. Okay, so that is it right here. This is what we have found. This is the equations of a free fall. So the vertical as a function of time, the location, horizontal, vertical location as functions of time, they live an independent life, because this is certainly the big idea was at some point in physics that you split, you decompose your motion into horizontal and vertical separately, because the physics is so different. The horizontal, there is a vertical force and there is no horizontal force, and so then things just split up, and then you can study them separately. So let's do that for a moment. So if I have t here and I put x there, what does the graph of this function look like? Of x? X is a function of t.
Oh, it's just a straight line.
A straight line with a slope,
Constant slope.
right? So let's say this. So then this will be px, the initial location, and then slope is dx. Okay? So different for the other one, for y, t and y. Okay, so it starts at some p sub y, but then what happens?
It goes up, it goes down.
It could, unless you throw it down, right? So I mean, if I start up on a building, I could actually throw it down if I want to. But suppose I throw it up, then what's the curve?
Negative 16.
Yeah, that curve, right? But I'm wondering if you know what looks like and what's called.
You're gonna have a maximum.
Yes, right.
And it's gonna go down until it hits the ground.
It might, if there's a hole there, it will just go down there. Okay, so you know the name of this curve, right? It is a parabola. Okay, so let's see. Okay, can you point out where v sub y is?
Is that the maximum?
No. The maximum is we're just getting to that. How to find the maximum?
Isn't that the point on the y-axis?
It is not the point, but this is on the y-axis, because that's where initial moment is, where time t equal to 0, it is where t is equal to 0, so it is on the y-axis, that point, but where is v sub y exactly? The point is p sub y, that's the location. What about v sub y?
Isn't that like the displacement of it, like the horizontal shift?
No, no. V sub y is the initial velocity. Can you see the initial velocity on the curve? Look at the initial velocity for x, right? It is the slope of that straight line. Well, this time it's not a straight line. So
The first tangent line?
the first tangent line, that's right. So the slope is v sub y, okay? So and once again, if v sub y is negative, it will go straight down, not straight down, but it will be also a parabola, a piece of a parabola, but going down. Okay, so that is almost it, but not to be mistaken of what we are not seeing these pictures. If you look at the ball thrown, you cannot see you cannot see this, neither one of this, because these are two functions of time. You cannot see time. Okay, so if the question is what is the path of a thrown ball, we know the answer is a parabola, but it's not that parabola exactly, because the parabola that we do see is x and y. Okay, so we have on the right we have t and y. Okay, so once again, that is a kind of it is an abstract graph where we imagine that as if the time has passed and we got the whole trace. But how do we get this x and y like this? So we put these two together to create it. Okay, it is in fact, we have done this before, and it is like a scatter plot in Excel, remember? So you have each of these functions is two columns, t and x, and then t and y. If I only pick t, x and y, I'll have the other graph. Okay, and it looks similar to the original, just not quite. It will still look like this. Why is it a parabola? Well, it's very simple. The idea is to get from these two here. What we do is eliminate t. You see what I'm talking about? Eliminate t from those equations. You see what I'm talking about? So I take my y and I want to express it. Look at that graph there in terms of x, not in terms of x, in terms of t. So how do I do it? I solve the second equation for t and substitute it into the first equation. So I take from the second equation, I have t equal x minus px divided by dx. Okay, substitute into the first one. And what do I get? I have y equal negative 16t, so this expression x minus px over dx squared plus v sub y, x minus px over v sub x, and plus p sub y. So we're not going to use this complex equation. The point of this only to make sure that we see that what we end up with, well, with all the complexity, it is a parabola. You see why this is a parabola?
Two variables still squared.
The highest power of x is squared. Okay, so which means it is a parabola. So that's why it just happens to be a parabola, and the reason is because the substitution is so simple that if it was quadratic with respect to t, then it is still quadratic with respect to x. That's all. So that confirms it. Before we do that, I want to show you this. If you haven't seen this yet, there's a little demonstration. Okay. Apparently in the Middle Ages, some people thought that the cannonball moves along a triangular path like that one. First it climbs by a straight line, and then when it reaches the highest point, it drops down on your head. Okay, which is now it's hard to imagine, but really, if what that's what simulation is about is what the shooting a cannonball from behind the cannon looks like. Okay, so let me just show. Okay, so let's just run it.
They just didn't account for the cannonball like shrinking as it went out in the distance, or
No, they just used it. Well, let me just run and you'll see it's really quite revealing. Look at the cannonball, going up, slowing down, slowing down, slowing down, slowing down, slowing down, slowing down, still slowing down, and then stops at the highest point. Then it starts to drop slowly. Slower at first, and faster, 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 right? So even though the whole thing is modeled, and then until it hits this thing, okay? So from behind, because you don't see the curving if you're standing right behind the cannon, you cannot tell exactly that it is a curve. It could be a straight line, and it just follows a straight line in this kind of weird way. That's what the triangle showed. The altitude is exactly the same as in the true picture, the parabola we just discussed, but it just you can't imagine that you're moving along a straight line if you just imagine that it's not moving at a constant speed, but rather climbing, slowing down up until the highest point, and then the last part as if somebody had dropped that ball from the highest point and it drops down. So it is actually quite plausible to imagine that somebody could be mistaken to describe the motion in a triangular fashion, especially if you... The question?
So like back then, did mathematicians believe that the force in the x and the y direction were both being reduced to the point to where it would hit its highest point and then just drop?
They did not. That's the trouble. They did not speak in terms of forces until Newton. Nobody had that even the idea. They did not have coordinates either to speak of. And so velocity was not well understood. It was still before Galileo. You know, the Galileo, that the one had actually demonstrated that two objects of heavy object and lighter object fall at the same speed. That he demonstrated that. So that was still before that. So they would think that a heavier cannon will go faster, or faster. So because they would you look at it like a feather and it's slowly falling, okay, so in comparison to like a cannonball or anything heavy, and so you can compare that. Of course the heavier object falls faster, okay, so that was the analysis, and they thought it goes faster, and so it all was messed up, and you can't really experiment until you take you put it in a vacuum. Have you seen this experiment? In a vacuum tube you put a feather and then a heavy object, doesn't matter, like a BB or something like that, and then you turn it, and they simultaneously hit the bottom.
You know, I never got why they compared it to a feather. Why wouldn't you say like a ping pong ball versus a bowling ball? You know what I mean? Because
no, you're talking about the ancient times or now?
Well, now, because like I remember whenever I was in like middle school and stuff,
Yeah.
they talk about gravity and they compare it to a feather, and I'm like, why wouldn't you pick something that doesn't, you know?
Well, but I
actually
think
go
it is
over air?
especially impressive. That is the they're refuting the ideas from the Middle Ages, and that's how they thought in the Middle Ages. They would look at a feather, the lightest object, and then some kind of bullet, say heavy object, and they would drop them, and obviously the feather would arrive later. And so they're refuting that idea by using really, really light objects such as feather, which used to be used to prove that the speeds are different. Okay, so they put both of in a vacuum, and then turns out something that we've seen always takes so long to get there, well, falls as fast as a bullet. So that's the idea, I think. Well, why you want to pick feather, and why they in the Middle Ages they never thought about the air resistance, which is actually, I was just about to say that with air resistance the trajectory is not as nice as a parabola. You know what the trajectory looks like under air resistance. And
Is the first half shorter than the second half?
the short No, the second is shorter. So it slows down, and then by the air resistance, so it looks like this. So it's almost the same, and then like this. So it's look more like that triangle. So the point is that it wasn't easy, and proving that otherwise wasn't easy. In my other class, I asked students to try to prove that the Earth is not flat, and it's not easy either. So if you how do you prove it? So and similarly here. So if you try to actually prove that the object follows a parabola, that takes experimentation. So that Galileo did it. He dropped a bullet and a cannonball. So the difference in weight was huge, but he did drop them simultaneously from that famous Tower of Pisa, and they dropped simultaneously. He saw it, and then he discovered that it probably grows quadratically. The time grows quadratically. That was the first idea, but that was after that somebody actually figured out that it was probably a parabola. And it was one of those mathematicians in Italy who was working on cubic equations. So you can see they didn't really have too many choices for curves. So whenever he looked at the cannonball shot, and then he thought looks like a curve, not a straight line, and then he thought it's probably a parabola. But they didn't have too many curves to begin with. So they had parabola, hyperbola, and ellipse. That's pretty much all the curves they knew at the time. So they just, like I said, they were just trying to solve the cubic equation. So they were early in that development. So I think it is kind of plausible that somebody would make such a mistake, even though it certainly they had weapons of this kind for siege way before Middle Ages. So Romans and Chinese too had all the kind of, they were not cannons, they were like trebuchet, like thrown with counterweights. And so you think you should know, but apparently, like you're stating, if it shoots far enough, it goes on, and then it kind of drops. It's totally plausible. And so somebody to refute this idea, you'd have to stand on the side, which not too many people would. Right? So it's more likely the gunner who makes all the observations. Anyway, so that was the point that development of science, how hard it is, and what I was going to do next is well, I'm just trying to remember if we did do it, but it was a while ago. So I'm trying to find that the scatter plot that is produced from, maybe it's here, from that site. The scatter plot that is produced from two functions. So you plot one function as I did, and then with Excel, and then you make the other one, and then you have four columns, but you then combine the last two. So tx, ty, and then these are two graphs, and then you combine x and y, and that gives you the graph of the function. So that is something that you can see. Well, probably I could find some of that. Yeah, it should be here somewhere. Well, that is one. Let's see. Let's think about it. Okay, so y. Okay, so this is a quadratic function, except instead of plotting them separately, I plotted them together. So here I keep combining x and y. Just a minute. Well, I guess this is okay. point. Okay, so I'm plotting x as a function of t. Doesn't matter what the formula is. We picked the free fall formula, so that is just one possibility. But you can combine. You can have dependence of x on t anyone that you can imagine. So that's just one of them. So suppose x progressing in time in this fashion. Okay, so based entirely on this table. What the formula is, it doesn't matter because it works for any formula. Okay, then what happens is I do the same with y. Okay, so that's my formula based again on t and y, like this. Okay, and well, let me change the type of the this one, this one. Okay, so two curves, x as a function of t, y as a function of t, and then the last step is right here. It is how does that work? Maybe this one. No. This one. Okay. This one is better. Okay, so I'll kill this one. Okay, so what is the last one is a combination of the first two. So if I click on this one, you can see as I told you, the x column is taken and the y column is taken. They are paired up, and each point x, y is plotted. For example, the first point is 1, x is 1, y is 1. Okay, and then I plot the point 1, 1 is plotted. This is point 1, 1, 1. Okay, the next point is x is 0.83, y is 136. That is the second point over here, right here. And then we keep plotting in that fashion until all the points that we need are taken care of. And then we have the last chart is, and that is the point that I've been making, is that it is a chart of dependence of x on y, or y on x, the relation between them, and we can be moving, in fact, that looks like a graph, but reality is we are moving from right to left, because the t is not present. These are, both of the x's are the x and y axis, and you can actually see you see the arrow over there. So that's what it is. In fact, I can probably change and make it more complicated. Say puts here something like let's put some sign here maybe, in order to make the point that we are talking about functions that are paths or trajectories that might be complicated. Okay? So once again, the graph on the left, x is a function of t. This is the function of y is a function of t. This is the relation between x and y. Okay, so the object then goes like this on the plane. So it's a horizontal motion within a horizontal plane, but the t parameter is not present because we excluded it. You can exclude it either algebraically, as we did over here, eliminating t, or you do it algebraically, or you do it numerically simply by look at it. I'm not using t. See, I'm using x, I'm using y, and that's all I need to do in order to plot them point by point. That's a scatter plot. How Excel does scatter plots. Okay, so that if you do any kind of motion, that's the way to go. Okay, so this is it's called a parametric curve. Okay. All right. So integration as an algebraic pursuit is going to be big, but not just yet. So we'll just concentrate on things that we can handle. So we have a few formulas, and we have some experience from differentiation, which is still to be worked all the way through in order to actually be useful. But we'll keep coming back to this. As we're studying differentiation, every time we do something about differentiation, we'll be coming back to anti-differentiation to see what is that we learn, if anything, new about it. Okay, so the next topic is, in fact, is more theory, but before more theory, we do some fairly practical topic, and that's optimization. So one topic of optimization we just examined, it was brought up a minute ago, and this is the question is right here. Where is the highest point? Okay, so certainly we have formulas, and we can plot them, just as you can experiment with data very easily, and it will tell you. For example, if you have data, like I said, this is sine, so you can guess. Or you see, this is a sine function. Okay, so the sine is plotted. This is sine. Where's the highest value? The highest value of sine is 1. What's the highest point? The maximum point. What is the value of x that gives you the largest value of sine? 1.6. It's actually, yeah. That's true. That's what data tells you. But in fact, you can do better than that if you just remember what cosine is, what sine does. At what point does it? You remember it is a rotation, right? At what point does it reach the highest point? Close to 1.6, but it's pi over 2, right? So 90 degrees is where the highest point is. So we could have discovered that by simply say I could try to make this value smaller, and once again the examination would by simple examination I would discover the more and more accurate value for this number. Okay, so for example, I put 0.1. Okay, so that's the highest point, and you can see that instead of 0.6, it still looks very much like 0.6. But we know that it's pi over 2. So more and more accurate values of x. Well, let me do more. So I want to see pi over 2 there. So I put here how about I put 1 here? Okay, so now you can see it's not 0.6. What's this? It still looks like 0.6. Okay, I got to do a better job. Okay, so as you can see, it straightens out, and now I put here 1.55. Okay. So this is the highest point. Okay, now you can see that it's not 1.6. 1.6 is right here. Okay, and the value is not the maximum. Maximum value is here, and it's 1.67 roughly. And that is already closer to pi over 2. Okay? So that always is an option. If you have a function, you want to do optimization with it. What do? You can plot it, and will give you the rough value of the maximum. So that's what we're about to do with the next problem. Let me come back. Okay, this is the problem we're going to be trying to solve. Suppose a farmer has 100 yards of fencing, and he wants to build as large enclosure as possible. Okay, so that's the whole problem. So that's another kind of word problems that we'll have to face. Optimization problems. Okay, so the plan is still the same. Translate everything into variables, introduce functions, and then solve it as an algebraic problem. So okay, so you have to figure out some of the things. For example, what kind of enclosure are we talking about? You don't want a circular enclosure, even though it might help, but let's say it's rectangular. So we're building a rectangular enclosure as large as possible from 100 yards of fencing. So how can we use that information? 100. So we have a rectangle here.
The total perimeter will be 100.
The perimeter is 100. Okay, so we're translating a little bit, and now the word in large refers to what, in your opinion?
To how large to the size will be. The area?
No, it's actually the area. It is the area because you know, you can stretch this way or that way. So we're looking for maximum area. Okay, so that's a one step into development of problem into mathematical statement. So it's still too much geometry. There are no variables, no functions. So let's do that. So suppose rectangle is, say, width and depth. Okay, and depth over here. So W by D. Okay, so that's the rectangle. And from that, so let's be specific. Better use words. W is the width, and D is the depth. Just like yesterday, remember, you introduce variables, explain them in words. So in fact, that's what we do. And then you use this as if it is a dictionary. Yeah.
Couldn't you take the square root of 100, because that'd be a square? Or no, you figure out, like, if the perimeter is 100, so each side would be 25.
Well,
and you divide the perimeter by 2, and then find the two values that add up to 50, the highest one that multiply together. You know what I mean?
yeah, but that's true. The problem is that once you change the problem slightly, then the insight, you're using some insight, and the insight is that the insight usually is just the square is the best choice. The square is the best choice for the area. It is the problem that goes back to a long time ago. I just read it again about it. It's like it's not a biblical story, but where is it? So this princess or queen was banished from her land, and she moved into this northern African area, and she went to the king, and she asked him to give me as much land as I could cover with a cowhide. And he said, okay, and she cut it into thin strips and covered a huge area. Okay, so then the most effective, by the way, is not a rectangle, but in fact a circle. And then the story tells that's how the city of Carthage started, apparently. So that's called the problem. I don't remember what it's called, but getting the largest area with a fixed perimeter. We are looking at the simplest problem imaginable when the region is rectangular. Because if it's not, the answer is actually a circle, and that is really hard to prove. You need more advanced mathematics than just calculus 1. So how do we demonstrate that the square, which is we just about to, why the square is the best? By the way, out of all rectangles, the square is the most round. Wouldn't you agree? So if you are bound to rectangles, then you pick the rectangle that is closest to the circle. And that is the square. Okay, so at least if we're gonna demonstrate in a minute with what we know that indeed we don't need anything but calculus to demonstrate that square is the best choice. If your perimeter is fixed, the best choice for the shape is a square. So certainly this is kind of plausible. Okay, even if you're not sure, you can actually a farmer might not have this insight. Maybe. So what would you do? And I would probably experiment. I would take a piece of paper. Even a farmer would know that you don't want to build enclosure, then measure it, and then build a new one, and then measure. So you would draw a piece of paper with various choices of width versus depth, right? And then just and then compute the area, right? So that's what you would do, like this. So for example, I would try. So I have 100. So I could try how about 10 by 40? Is it that's right? So it adds up to 10, 10, 10. So it will be 10 like this, 10, 10, 50, 40, 40. Okay, that works out. Okay, so the area will be 400, right? And then you keep going, then you try, say, 15 by 35. What the hell is that? 525. So as you can see, you're improving. Okay, and then you try 20 by 30. 600, even better. But then if you skip the next step, then you get to 30 by 20, and it is 30 by 20, which is again 600. That gives you an idea that maybe somewhere in between there's a better choice, and you hit 25 by 25, and that will be the right answer. And then you realize, well, squares is the best. Of course, why didn't I think of that? But at least on a piece of paper, you can work that out pretty well. If not, you do a spreadsheet just as well. So once again, all the possible rectangles with a given perimeter, and just compare the outputs. That's no trouble. So, but and it is certainly a totally legitimate way of doing things. When you have a problem is specific, when all the numbers are specific, you could do it problems in trial and error, numerical analysis, and so on. Anything goes. But in next time you change the problem slightly, and what if perimeter is unspecified, and you want a problem, there are some parameters that have not been specified, such as the perimeter, for example. And even if you solve the problem on the right, and you know that if you have 100 yards of fencing, then the best answer for you is 25 by 25. But what if now I have 200 yards of fencing? What's the best choice for me? 50 by 50, because it's again a square, and then if I have now 1,000 yards of fencing, then I also know that what it's supposed to be. That is then once you realize that, you conclude that it should be a square. You're doing mathematics. You're not just doing farming. If you conclude that the square is always the best, that is mathematics. That is literally doing mathematics in the most narrow sense of the word. Discovering that the best shape, rectangle shape for give you the largest area is a square. That's a mathematics. So, but you cannot finish the job in mathematical job but for experimentation only. That's why you have to do analysis. You have to look at the function with infinitely many possibilities. So 25 by 25 is a good idea, but what if they're just a little bit off, 24 by 26? Yeah, you didn't check 24 by 26. Maybe it's better. Well, maybe it's not. Maybe there is a number somewhere hiding that it is better. So so you have to do it in an abstract way. So you have to define a function with these variables, and then optimize it, find the maximum point on it. So let's run this quickly. So rectangles W by D. We're talking about the area. I introduce a new variable. A is the area. And then what I have on the right, is I need to maximize. So maximize A. Maximize A. Okay. On the left, okay. On the left it is a statement. Perimeter is 100. So, as it is always the case, and that is, by the way, something that I encounter so many times, that since the test is coming, I want to warn you that you gotta have the equal sign. So when you do computations, use the sign equal sign. Why? Because equal sign stands for it will replace that word over there in the middle, is, and vice versa. Okay, so if you have a sentence, you write it. If you rewriting it algebraically, there will be equal sign in the middle. Whether you're solving equations, you carried out computations, simplifications, you have to have. So I just seen this too many times to be just to want to see it one more time. So 1 plus 1 is equal to 2. It's not 1 plus 1, 2. You see what's missing in that sentence. 1 plus 1, 2. What's missing? The word is missing. So either you You know, up until like 14th century, they did not have equal sign, or even later, I think. So they would write in words, and then there's no confusion then in what you're saying. So either this way or is, and at some point, by the way, try to guess. I just recently found out where the equal sign comes from. It is actually it comes from an English word. All these symbols, plus, minus, they all were invented by Italians. But with the equal sign, the last drop was the last missing piece of the puzzle to have everything algebraic is the equal sign. And the equal sign comes from the word equal. You see how? Impossible to guess. I wouldn't have guessed. Because they used to spell equal with two L's. Equal, L-L-E at the end. Okay, so he just took those two L's and turned it. Who knew? That is just fascinating. So anyway, so algebra used not exist. Okay, so everything was a sentence. So nothing has changed. There's still every computation is a sentence. So you look at the book, or you look how I write. Anybody who is writing anywhere, the equal sign is everywhere, and if it is missing, then the word is here somewhere. So sentence should be complete, just as it's just grammar. Mathematics requires grammar as well. So my sentence then becomes what? Perimeter is equal to 100. I don't want to introduce a new variable, or I might. It's a little bit of an overkill if I introduce another variable, or I can just write what perimeter is in terms of those variables. What's the perimeter?
2w plus 2d.
2w plus 2d is equal to 100. Okay, so that is pretty much it. In fact, I could now circle what the problem is. Actually the problem is much smaller. What's in the middle, it is the dictionary, the translation, and it is referring to the previous picture. At this time, we don't really need the picture except maybe to mention that probably these variables should be larger than or equal to 0. So just to keep get into some weird stuff, which happens sometimes. You're discarding the geometric information, and I just did, and then you might be producing a solution that doesn't make any sense. Of course, you can solve it and then verify it, or you can just you can take care of it early on. So I'm taking care of it early on. I have an equation. I have two variables. Three variables. The third one. The third one. I still have a missing puzzle piece, and that is the area is the product of the width times the depth. Okay. So let me write it one more time. So the problem now becomes purely algebraic. Maximize A is equal to W times D with a restriction. 2W plus 2D is equal to 100. So that's the algebraic representation of our problem. And at this point, you can do the way the farmer did, and you vary W and D arbitrarily, and then create a table of areas. Okay, so you can do it like this. W here, D is here, so 0, 1, 2, 3, and then compute the area here. Okay, that is a lot of wasted time because you will be computing the areas of rectangles that are of no interest to you. Say 10 by 10. What's the interest? You are wasting your fencing. If you have 10 by 10 or enclosure, you are only spending 40 yards of fencing. So there is really no interest. On the other hand, if you have 100 by 100, it's too large. You don't have enough fencing for it. So it better take care of it by how do we get rid of those possibilities that have no interest for us? How do we simplify the problem? So this is, if you think about this, is a kind of a function, except the inconvenience is that it has two variables. We have been studying functions of one variable. So if we have a function of two variables, we will we'd rather study functions of one variable. What do we do?
Try to eliminate.
We eliminate one of them. So eliminate one of them. Okay? So, so once again, the function to be maximized, followed by a constraint. So the constraint is what we use to eliminate the variable, right? So we only have two things: the function that we gonna deal with, and then there is this constraint that that we use to. It is a connection, a relation between the two variables, and we can use it. So I have 2w plus 2d is equal to 100. I divide by 2. W plus d is equal to 50, and w is equal to 50 minus d. Okay, so that expresses directly, explicitly one variable in terms of the other, and I just substitute it into a. So I have a is equal to w times d is equal to 50 minus d times d. Okay, which is 50d minus d squared. So let me restate the problem. Maximize a equal to 50d minus d squared. At this point, you can't think of a as a function of d, one variable, right? So
It's quadratic.
it is a quadratic formula. Let's start to solve it. So it's quadratic. So what does it tell us? If the function is quadratic, so its graph is a parabola. Can you tell more? What kind of parabola?
It's going to have a maximum.
Yeah, it is an upside down parabola. In other words, parabola that opens down. How do we know that?
Negative d.
That's right. So because the term is, remember what it is called? The leading coefficient is negative. So generally speaking, this is what it's going to look like. Okay, which is good news, which means that that's the good news, there is a maximum. So, you try to optimize the problem, it's quite possible that there is no nice solution. Okay, that you don't know ahead of time. If the more practical problem it is, the more real life problem it is, the more likely it is you don't have anything, any good solution there. But this one does. So that is the point. How do you find it?
You factor.
No, I don't think so. I don't think you want to factor it. Well, what do you know about the shape of the parabola? What's the relation between one branch and the other branch?
They're symmetric.
They're symmetric. It is symmetric, which means, so the graph is symmetric. Specifically,
So there's got to be the same amount of x values on each side.
as on the left, right? So symmetric. So there is what we say is there is a vertical axis of symmetry. This one. And to the left is the same as to the right, so all remains, and that is the point that we're looking for. So it will pass, that line will pass through the tip, and where is that? It lies then halfway between what?
Between the zeros.
The x-intercepts. Same thing. So between these two, one and the other. One is 100. One is 0, and the other 100. Right. 0 and 100. So it's 50. hold on a second. It is 50. I'm sorry. I'm looking in the wrong place. The other x-intercept is 50, right? And well, in that sense, yeah, actually, you do factor it. To find x-intercept, you do factor it. This is 50. Well, we already had it factored. Here it is. So it is factored, and that's how we know that there are two x-intercepts, 50 and 0. So then the answer halfway is 25. Okay, so the answer is then 25 over here. 25.
How does the area underneath the maximum to the x-axis relate?
The area, I don't think area is
Does that
comes
relate
into
to
play
the
here.
area of the square
What?
or fence?
No, the area, where is the area? This is the area. This is D. So area is a function of the depth. D on the x-axis, A on the y-axis, and in the highest point on the graph is what we're looking for, right? So the answer is 25. Clearly, from the picture, we used a little bit about what we have learned about the about parabolas. They're symmetric. They're upside down whenever the leading coefficient is negative, leading coefficient or leading term is negative. And then we find there is a formula. It's really not that hard to find the formula for the what we say the vertex of a parabola. Okay, but this works out pretty well. This is solid proof. It does rely on prior information about the shapes of parabolas, but it is all fine because that information goes back to like ancient Greeks. They knew everything there was to know about parabolas, even though they did not know algebra nor coordinate systems, but they learned a lot about parabolas. So before we move on, alternatively, that's really not the way we want to do it, because it is just we were lucky that the formula was the function was quadratic. And then next you step off and it's not quadratic anymore, and we cannot use the information about the parabola. Okay, so that's really not a lesson. The lesson is well, there is no lesson yet, but let's see what should the lesson be if we're looking at that graph and we do not know anything about the symmetry. So suppose this one is gone, this information. So how would we find that top point? So without this, what do we do? Well, you can still do numerically, right? That number one, that's what the person, the farmer would do, and we can totally do it with any function that you can imagine. You can plot it, you can examine it, and you will have the answer, which is more or less satisfactory, but practically speaking, but mathematically not so much. So let's take a closer look at the graph and what's so special about that point. In addition to being the highest point, but
Optimal.
it is, yeah, okay. How about we zoom in on it?
Well, the slope's 0.
The slope is 0. Zoom in on it, and we discover that slope is 0 indeed. So we zoom in on it, it will look like this, right? And the tangent line is 0, slope is 0, which means that f dA dd, the derivative of the area with respect to the depth is 0. That's how we know we can, and then that would work with way many other functions, with the one that have no symmetry whatsoever. That plan will work. Just look at the points where the derivative is equal to 0. Let me confirm that. So if I take my function over there, 50d minus d squared, 50d minus d squared, I differentiate with respect to this variable d. I have 50 minus 2d, set it equal to 0, solve. With very little algebra at the very end, I solve this problem, and d is equal to 25. Okay, so that's how we do optimization problems with calculus tools. So derivative comes into play to give us the highest lowest point. It's also possible that we try to minimize things, and that's what it's going to give us. Just I want to do one more thing before we go home. The alternative problem, the slight variant to this problem is to what if the what if the enclosure is built next to a river? You have a river, and you're building still an enclosure, still 100 yards of fencing, but you don't need the second, the third, the fourth wall. Okay, so can you see what it would change? What would change?
It would be 33, 23. It'd be a third of 100, wouldn't it? Each
Well,
side?
why do you think it's 1/3?
Because it's got to be a
Are
square.
you see that's your intuition totally fails you. It's not going to be a square anymore. Well, let's solve this problem quickly. Probably won't. Since this is already solved, we can do it quickly. So what is at the very top? What do we have to fix in order to have this new problem? Area is still W times D. Okay, so this is still D and this is W. What do I do? The second. What's the constraint?
W plus 2D equals 100.
Say it again.
1 W.
1W. This will be gone, right? Okay, so then when we substitute, it's gonna be well, what our function becomes. Our function becomes a is equal to 100 minus 2d times d, right? Okay, or 100d minus 2d squared. Okay, and let's quickly differentiate. What do we get?
100D minus 40.
Hold on a second. Yeah, 4D. Yeah, okay, so D is equal to 25. So it is actually 25 by 50. Who would have thought? Impossible to guess. Impossible to guess. The problem is really very different. It's not clear that right away that the problem is different, but it is. Okay, so we'll do some more of this next time.